Fractional calculus generalizes the concepts of integrals and derivatives to non-integer orders, which means fractional derivatives and fractional integrals, collectively known as fractals. This allows us to explore new dimensions of calculus, and this has various applications in engineering, more particularly fluid dynamics, and in physics as well. A cornerstone of fractional calculus is the Riemann-Liouville integral, named after two French mathematicians, I think, Bernard Riemann and Joseph Liouville. This integral extends the idea of repeated integration to fractional as well as real orders. This expression defines the Riemann-Liouville integral of order n greater than 0. On the left, you have Inf of x, which means the nth integral of the function f. And this is the expression of the Riemann-Liouville integral. Or better still, this is the expression of the repeated integral of a function n, of a function f to the order n. You can see that this expression contains the gamma function, defined thus, okay? And for positive integers, n, we can show that gamma of n is equal to n minus 1 factorial. So what we want to do in this video is to prove the Riemann-Liouville integral by induction. There are other ways by which we can demonstrate this proof. It's not very complicated, but in this video, we are going to do that by induction. So already, let me write explicitly what In of f means. In of f means an integral, okay, an nth order integral of the function f, let's say f depending on t. So let's say f of t1, dt1, dt2, dtn, and then you put the corresponding boundaries. So In of f here means you are just integrating the function n times, okay? And what I will show here is that this is equivalent to what we have on the right hand side. The method of induction, just to recall, involves 3 essential steps. First, you need to prove that this expression holds for the base case. That is the first step. Then we are going to make a hypothesis and assume that this function or that this expression is true as well for any integer k. That's known as the induction hypothesis. And from there, we are going to prove that the expression is also true for n equals k plus 1, which means the term in front of n equals k. So let's start with the base case. So base case, we have n equals 1. So if n is equals to 1, let's replace 1 in this expression. We're going to have that I1 of f of x is equal to 1 all over gamma of 1, okay? Integral from 0 to x of x minus t to the power 0 times f of t dt. If we simplify this, gamma of 1 is just 1, and x minus t to the power 0 is 1. So we are having the integral from 0 to x of f of t dt. And we can clearly notice that this is just a single integral of the function f. So this expression here is just I1 of f. Okay, so the statement holds for the base case. Then we are going to make a hypothesis, the inductive step, and assume that this expression holds for any integer n equals k. Okay, which means that if we replace any value of n here, let's say k, this should be true as well. So we can write that as In of, so Ik of f of x equal to 1 all over gamma of k, but I'm going to replace here gamma of k by the expression of the gamma function of an integer k, which is just k minus 1 factorial. So here we are going to put k minus 1 factorial. Then the integral from 0 to x of x minus t n minus 1 f of t dt. Okay. And then from here, we are going to prove that this is also true for n equals k plus 1. So we prove then for n equals k plus 1. In this case, we are going to have I k plus 1 of f of x is going to be equals to 1 all over gamma of k plus 1. But again, we are going to replace gamma of k plus 1 by the expression. So it will be k plus 1 minus 1 factorial. So that's going to be k factorial. Okay. Then the integral from 0 to x. Okay. And then x minus t to the power k, because we put k plus 1 here, times f of t dt. So this is what we want to show, okay, based on our induction hypothesis. So how do we do that? We can realize that the k plus 1th integral of a function f, so I k plus 1 of the function f of x is actually the integral of ik f of t dt from 0 to x. Which means that if you integrate a function k times, and then you integrate that result one time, you're going to get the k plus 1th integral of that function. Okay? So it's really intuitive here. So we can then replace the expression of ik of f from our inductive step. We can take this and plug it here. And that's going to give us the integral from 0 to x of 1 on k minus 1 factorial. Okay, maybe let me just put a parenthesis here. And then we need to plug in all of this. Just that we need to be careful because this expression was expressed in terms of the variable t. And then here we also have another variable t. So we need to change the variable here in order to avoid any ambiguity. So let's say we decide to, instead of putting t here, let's put u. So we have x minus u to the power k minus 1, okay, times f of u du, and then this result has to be a function of t. So the boundaries I'm going to put from 0 to t, okay, and then here we have dt. Hope that's clear. So we're going to put this out of the integral. That's going to give us 1 on k minus 1 factorial integral from 0 to x. Okay. Now we have the second integral, which goes from 0 to t. We have, and then we have t minus u. Okay. So actually here it's t and not x because we changed that variable to t. Okay. So t minus u to the power k minus 1 times f of u du, and the result with respect to t. So at this point, in order to be able to simplify this expression, we are going to do what we call a change in the order of integration, which means that instead of integrating with respect to u before integrating with respect to t, we are going to first integrate with respect to t. So we are going to bring dt inside here and then pull f of u du outside of this expression. It's easier to integrate this first with respect to t because here we just have a polynomial expression and we easily know what's the integral of a polynomial. So we're going to rewrite this as 1 over k minus 1 factorial integral from, I will not put the boundaries for now because we need to figure them out. If we are changing the order of integration, we need to change the boundaries as well. So I'm just going to put integral here. Then here we have t minus u to the power k minus 1. Then we have a dt, okay? And outside we have an f of u du. So we need to figure out now these boundaries. And the way we do that is by simply recognizing that in this expression, we first ought to perform the integral with respect to u, and u was going from 0 to t. Hope you can see that. So u goes from 0 to t, and then we perform an integral where t goes from 0 to x. So t goes from 0 to x. So this is actually like the rank or the order in which we have to integrate the variables. So we can see that u lies between 0 and t lies between 0 and x. So based on this, we see then that if we want to perform the integral first with respect to t has to go from u to x, okay? So like that. And then the second integral, which depends on u, has to go from 0 to x. Okay? Hope you can see that. Hope it's clear. Here, it's not very straightforward, but it's important to understand this change of variable. So then we are going to perform that integral. Let me take another sheet of paper. We're going to have I k plus 1 f of x is just going to be equal to 1 on k minus 1 factorial times the integral from 0 to x. Okay? Now, in order to integrate this expression inside here, you see that this is just a polynomial. Okay? If you're integrating a polynomial, you can just apply the integral for a polynomial. So that's just going to be t minus u to the power k minus 1 plus 1. Okay? And then divided by k minus 1 plus 1. So the result of this is just going to be x minus u to the power k all over k. Okay? That's just the result of this integral. Hope that's clear. Then we put in the boundaries. The boundaries go from u to x, and then we add f of u du. And if we substitute those boundaries, we can simplify this further as integral from 0 to x. This is going to remain x minus u to the power k on k. Okay, if you substitute the boundaries, and then you're going to have f of u du. So what you see, we can bring out this constant k from the integral. That's going to give us k times k minus 1 factorial, and k times k minus 1 factorial is just k factorial. And here we are going to be left with x minus u to the power k times f of u du. And you can realize that this expression over here is exactly what we wanted to show. It's exactly this one, okay? Only the variables have changed, but the expression of the integral is exactly the same, which means that the statement holds for n equals k plus 1. And that's I k plus 1 f of x. And this completes the induction step and thus proves that for any integer n, the Riemann-Liouville integral of order n matches the n-fold iterated integral, which is what we wanted to show. Okay? So this expression is correct. So hope you find that interesting. Okay? You can enter your remarks in the comment section. I'll be glad to read you as usual. Let me know what you think of the Riemann-Liouville integral and fractional derivatives or fractional calculus as a whole. And I see you in the next video.